So in the previous lecture, the topic of work and energy kinetics of the particle was started. Few equations were developed. The equation of work energy principle, then the equation for the work due to the weight of the object, and the work due to the spring force. So equation number 1 is the work due to weight of the object, and equation number 2 is weight is due to the spring force, and the third one is the work energy principle. The symbol T is for kinetic energy, symbol U is for work, and over here W is weight, delta Y is change in elevation or Y distance, and S2 and S1 is the displacement of the spring. The next topic is conservative force. The definition of conservative force, that it is the force whose work is independent of the path. The work obtained depends only on the initial and final position of the path. The examples of conservative forces are weight of the particle and force developed by the spring. That is, the work associated with the weight of the particle will depend on only the elevation difference. It will not depend on the path, whether the particle moves from top to bottom in a vertical path, and on the other hand, if the particle moves from one point to the other by taking a complicated path, the calculation of work will only depend on delta Y, whether the particle moves in vertical path or some complicated path. Similarly, the work associated with the spring force will only depend on the initial position of the spring and final position. So these two forces are conservative forces. The example of non-conservative force is the friction force. If the particle moves from one location to the other, the work associated with the friction force will not only depend on the final and initial position, it will depend on the path. If the path is longer, then the work required or the work associated with the friction force will be more, and if the path is small, the work associated with the friction force will be small. So example, friction force is an example of non-conservative force. Now, definition of energy, it is the capacity for doing work. If we consider equation number 3, suppose the particle initially is at rest, then in that case T1 will be equal to 0. Then summation U from 1 to 2, which is the work done, will be equal to final kinetic energy. So we can define kinetic energy. It is the measure of the particle's capacity to do work, and it is associated with the motion of the particle. Then another form of energy is potential energy. Potential energy is due to the position of the particle. For potential energy, we always require datum. We determine the potential energy of the particle or any object depending on the position and depending on the distance from the datum. The potential energy is created by the weight of the particle and due to the elastic spring. This means that there are two common examples in mechanical engineering. for the potential energy. One is the weight, due to the weight of the particle and due to the elastic spring or the elasticity of the object. The symbol used in the book is capital V. Capital V is for potential energy, and the subscript G is for gravitational potential energy, which is due to the weight of the particle. So we can see the schematic. Suppose the particle is at datum. In that case, the potential energy, gravitational potential energy, will be equal to 0. If the particle is at higher elevation, then the potential energy or gravitational potential energy will be positive. If the particle is below datum, then in that case the gravitational potential energy will be negative. Positive gravitational potential energy means that when the particle will move from top to bottom, it will have positive work. Positive work means the direction of displacement and direction of force are same. So when the particle is moving downward, weight is acting downward, so it is negative, and displacement is downward, so both are negative. It gives the positive work. So when the particle is at higher elevation, it has positive potential energy. Similarly, when the particle is at lower elevation, below datum, then it will require negative work to move from bottom to the datum, because in that case displacement will be upward and weight will act downward. So we can write gravitational potential energy as Wy. We can replace delta Y with Y, and gravitational potential energy can be written as Vg equal to Wy. So we can write gravitational potential energy Vg equal to Wy. So if Y will be positive above datum, then potential energy will be positive. If Y is below datum, then it is a negative quantity. The gravitational potential energy will be negative. Then we discuss about the elastic potential energy. The common example is the potential energy of the spring when it is elongated or compressed. From the previous topic, we know that the elastic potential energy is half Ks square. Elastic potential energy is always positive. The reason is that whether we are compressing or expanding, in both cases the spring will come to its original position. If we compress the spring, it has a tendency to return back to its original position. We will not require any external force. This means the elastic potential energy is positive. Similarly, if the spring is stretched or elongated, it has a tendency to come back to its original position. So in both cases, for coming back to the original position, we will not require any force or any work. So this means the potential energy of the spring, the elastic potential energy, is always positive. So we can see here in both cases the elastic potential energy is always positive. In comparison, the gravitational potential energy can be positive or negative. If the particle is above datum, it is positive. If it is below datum, then gravitational potential energy is negative. The total potential energy is Vg plus Ve, and we can name this as potential function. We can solve the above equations 1, 2, 4 and 5. We have 4 equations: gravitational potential energy, elastic potential energy. Then we have 3 more work energy principle and the work associated with the weight and work associated with the spring force. If we solve these 5 or 4 equations, you will get this formula. The work done by the conservative force in moving the particle from one point to the other, it will be calculated from V1 minus V2. To determine the potential function, that is the total potential energy of a particle, we will add the 2 potential energies and we can calculate both the potential energies for any case. This is an example in which the spring is in the vertical position and weight is acting downward. Since the spring is elongated, the direction of the spring force is opposite, it is in the upward direction. The spring moves from one location S1 to S2. In that case, the change in potential energy due to the weight or gravitational potential energy will be W multiplied by S2 minus S1. Similarly, the elastic potential energy difference will be half Ks2 square minus half Ks1 square. But if the displacement is small, suppose the initial position is x, y, z and the final position is shown with the term for the differential change, then the small amount of work will be determined from the change in potential energy at the 2 locations. So after simplifying mathematically, we will get minus dV at a location x, y, z. So this is our equation number 7. And from the beginning topic of this chapter, we showed that du equal to F dot dr, force dot product with the displacement. In force is a vector quantity, so we write 3 components, Fx, Fy and Fz, and then we write the 3 components for the displacement, dxi dyj plus dzk. After taking the dot product, we get the work for the small displacement. So now we have 2 equations. We have equation number 7 and then we have this equation. We can equate these 2 equations. On the left hand side, we have work in terms of forces, and on the right hand side we have the work due to the potential function or potential energy. dV is total differential. We write the total differential in terms of partial differentials, that is the change in potential energy can be split in 3 terms: change in x direction, change in y direction and change in z direction. When we solve this equation, after equating we get the force components in terms of change in potential energy. We can merge the three components and we can write in this form. And this is the del operator. We take the scalar gradient minus del V. The del operator is written with this symbol del, and when we take the gradient, when we take the simple multiplication with any scalar function, then it is termed as gradient. So force is expressed as a gradient of potential energy. So this is a mathematical description or mathematical criterion for the force to be conservative. If the force is such that it can be written in terms of a gradient of a scalar function, then that force is a conservative force. We can prove that the gravitational potential energy or gravitational potential energy or the weight is conservative. We can prove that weight is a conservative force. Since weight acts in the downward direction, we only write the y component of force by looking at the above equation. Fy is equal to minus dava v over dava y. In general we have three components, but for the weight we have only one component. So Fy is equal to minus dava v over dava y, but potential energy or gravitational potential energy is Wy. So we put V equal to Wy, we get minus W. After simplifying we get minus W. So the y direction force is equal to weight. We can see that the weight is written as a gradient of a scalar potential. The next topic is conservation of energy. Previously we showed that the work energy principle is kinetic energy or initial kinetic energy plus all the works is equal to final kinetic energy. Then work can be due to conservative force or it can be due to non-conservative force. Equation number 3 includes summation u, which includes conservative force work and non-conservative force work. So we divide into two components in equation number 9. But conservative force or the work due to conservative force is equal to V1 minus V2, which has already been calculated. By solving 6 and 9 we get equation number 10. Suppose there are no non-conservative forces, there is no work due to non-conservative forces, then we can ignore this term, and finally we will get equation number 11. So this is conservation of mechanical energy. The sum of initial kinetic energy and potential energy is equal to final kinetic energy plus final potential energy. Equation number 11 is for a single particle. If we have the multiple or system of particles, then we will write summation. In the mechanical energy, conservation of mechanical energy, we have kinetic energy and potential energy. The students have studied a similar equation in the course of thermodynamics, in which we have few more energies when the fluid is moving. When we consider the fluid, there can be additional energies. One is the flow energy, which is due to pressure, and the other one is the thermal energy or internal energy, which is usually due to change in temperature. Since the problem in the present topic does not include any fluid or any temperature change is not involved, the equation only includes the potential energy and kinetic energy. So sum of kinetic energy and potential energy is same. We can have a small example. Suppose a ball is dropped from a certain height h. The weight of the ball is W. When the ball is at a height of h, it will have some potential energy, and it is dropped from rest, so kinetic energy is 0. As the ball moves downward, the potential energy decreases and kinetic energy increases. When the ball strikes the ground, it has maximum kinetic energy and potential energy becomes 0. If we calculate the total energy, at the top position there is no kinetic energy, so T1 is 0 and V1 is WH or mgh. So at the top the total energy is WH. Now we calculate the sum of energy at the intermediate location. Suppose h upon 2. For calculating the kinetic energy, we use the simple equation of motion formula. Acceleration is constant, which is g. V naught will be equal to 0 and y minus y naught will be equal to h upon 2. So velocity is under root gh. We calculate the total energy. Kinetic energy is half m, and this is v square, plus potential energy, which is mg, and distance is h upon 2. The sum gives wh. Then suppose we calculate the total energy at the bottom location. At the bottom location we can prove that velocity is equal to under root gh using the same formula of equation of motion based on velocity and distance. Velocity is under root 2gh. If we calculate the total energy, potential energy is 0 and kinetic energy, after solving and simplifying, we get wh. So at all locations the sum of energy is same. Now suppose the ball strikes the ground, it will bounce back in the opposite direction. If the ground is hard enough, ball is also hard enough, it will rebound off the surface. It will have a new height. If there is no energy loss, it will bounce back to the original position. But there are energy losses, and due to losses the new height will be h dash which will be less than the original height, and the height is less due to the energy loss. There can be several sources for the energy loss. For example, noise, it is also a form of energy. then energy loss associated with the deformation of the ball and the ground, and generation of heat. So when the ball strikes the ground, there is some generation of heat, even though the quantity is very less and we do not feel any significant temperature difference, but there is a minor change due to small amount of heat which is produced. So due to these factors, the height reached by the ball is relatively less when compared to the original height. Okay, next topic is kinetics of a particle, impulse and momentum. There are 3 chapters for the kinetics of a particle in the book. One is the kinetics of particle with the study in terms of force and acceleration. Then chapter number 14 is kinetics of a particle when the quantities work and energy are described. And this is the 3rd chapter for the kinetics of the particle, in which the kinetics is studied in terms of impulse and momentum. The basis is same. The equations are based on the equation of motion, summation F equal to ma. A can be written as dv over dt. Then we can move dt on the left hand side, so this will give summation F dt equal to mdv. So for finding to solve this equation, differential equation, we will integrate. Integration for time will be from t1 to t2, and for velocity it will be from v1 to v2. Mass is constant, so we can remove mass out of the integral sign, and we will get simply mv2 minus mv1. Integral f dt can be evaluated if force is constant or force is written in terms of time. Equation number 2 is principle of linear impulse and momentum. When the equation of motion was converted in terms of work and energy by using A equal to v dv over ds, then that was principle of energy and work. But here we are solving in terms of time. So this is principle of linear impulse and linear momentum. So we can see from the equation, it is simply a time integration of the equation of motion. From this equation we can directly find the velocity after any process, after any collision, by directly from this equation. We use some symbols. For momentum, mass into velocity, we use a symbol L, linear momentum, and integral f dt the symbol is capital I. So capital I is for impulse. Basically it is a linear impulse. Linear impulse and linear momentum are vector quantities. So as I mentioned, the impulse can be calculated when force is written in terms of time, or if force is constant we can integrate integral f dt. If force is constant, then we can write Fc multiplied by T2 minus T1. We can see two cases. On the right hand side, the force is constant. When force is constant, capital I is equal to Fc multiplied by T2 minus T1. When force is variable, then we will write integral f function of time and dt. So unless we have the force as a function of time, we cannot integrate. After simplifying the above equation, that is, we move mv1 on the left hand side, we get the equation in some modified form. So this is equation number 3. It states that the initial momentum of the particle at time t1 plus the sum of all the impulses applied to the particle is equal to the final momentum. Initial momentum plus sum of impulse due to sum of all the forces, impulse due to forces, is equal to final momentum. This is the vector diagram. Since momentum and impulse are vector quantities, so mv1 is, suppose in the positive x and y direction, mv1 is the initial momentum, and there are some forces or impulses acting on the particle. It results in the calculation of the final momentum. The equation is a vector equation, so it will have three components. So if you have to balance the momentum and impulses in x, y and z direction separately. So impulse, the linear momentum in x direction initial plus the impulses in the x direction will give the final momentum in the x direction. Similarly, we have the equations in y and z directions.